Dear students, welcome to 27th online class of Control System Engineering. In last class we studied about PD controller or proportional derivative controller. With the help of PD controller, we can modify the transient response specification of a system. PD controller are made up of active components which require additional power sources, and it also have disadvantage of noise. Dear students, after this lecture you will be able to design a controller to improve the transient response or transient specification of a system. Dear students, contents of this lecture are lead compensator. A lead compensator is made up of passive components. Dear students, now we will study lead compensator. Just as active ideal integral compensator can be approximated with a passive lag network, similarly, an active ideal derivative compensator can also be approximated with a passive lead compensator. The advantage of passive lead network over the PD controller are no additional power sources are required and noise due to pure differentiation is reduced, where the disadvantage is that additional pole doesn't reduce the number of branches of the root locus that crosses the imaginary axis and enters into right half plane, where the addition of single zero of PD controller reduces the number of branches of the root locus that crosses j omega axis and enters into right half plane. Dear students, now for lead compensator, if we select the desired dominant second order pole on the S plane, then the sum of angles from the uncompensated system poles and zeros to the design point can be found, and the difference between 180 degrees and the sum of angles must be the angular contribution required of the compensator. Now look at the system given in the figure. The uncompensated system have two poles and one zeros. Poles are represented by P1 and P2, where 0 is represented by Z1, and desired location for dominant second order pole is also given, and respective angles for each vector are also mentioned. Now to this system for compensation we add a lead compensator, which have a compensator 0 and compensator pole, and their vectors are also connected to the desired point and respective angles are also given. Now if our desired point is a part of root locus, then it must fulfill angles criteria, which says that sum of angles of zeros minus sum of angles of poles must be equal to odd multiples of 180 degree. Here theta 1 represents angular contribution of compensator pole, where theta 2 represents angular contribution of compensator 0. So their difference theta 2 minus theta 1 will be equal to the angular contribution of lead compensator. From the figure you can observe that theta c is the angle of ray extending from desired point and intersecting the real axis at compensator pole and compensator 0. Or we can say that theta c is the required angular contribution for lead compensator to make the desired point a part of root locus. Students, now this can be visualized that the ray rotating about a desired closed loop pole location and intersecting the real axis at compensator pole and compensator 0 as shown in the figure. We realize that an infinite number of lead compensator could be used to meet the desired transient response requirement. And for this, we arbitrarily select either a lead compensator pole or 0 and find out the angular contribution at the design point of this pole or 0 along with system's open loop poles and zeros. The difference between this angle and 180 degree is the required contribution of the remaining compensator pole or 0. Dear students, in the given problem, we have to design 3 lead compensators for a system that will reduce the settling time by a factor of 2 while maintaining 30% overshoot. And we will compare the system characteristics between the 3 designs. Students, in the solution, first of all, we will sketch the root locus of the system. And for overshoot of 30%, we will find value of damping ratio zeta, which equals to 0.358, and for this, we will draw line of constant damping ratio zeta, which will have an angle of 110.98 degrees. Now along the line of constant damping ratio, we will find out the point where root locus will intersect this line. And the uncompensated system intersects the radial line at point minus 1.007 plus j 2.627 with gain of 63.21. And for this, we will have a settling time of 4 divided by sigma, which equals 3.972 seconds. Dear students, now we know that settling time of uncompensated system operating at 30% overshoot is about 3.972 seconds. Now we will find required settling time and location of dominant pair of poles. We required two-fold reduction in settling time, so our new settling time will be equal to about 1.986 seconds. Now we will find design point for this settling time. Using the relation of settling time, the real part of design part will be equal to minus sigma, which in turns be equal to 4 divided by settling time, or minus 2.014. Now the compensated system will also have the overshoot of 30%, which means that new dominant pole will also lie on the radial line. Now considering a right angle triangle and using trigonometry, the imaginary part will be equal to 5.252. Students, now in the problem we have to design 3 lead controller. For first lead compensator, we will choose the location of minus 5 for compensator 0 on the real axis. Now we will find sum of angles of uncompensated system poles and the 0 added at minus 5 to the new design point, and will find its difference with 180 degree. The sum of angles here equal 172.69. The difference between This angle and 180 degree is the angular contribution required from the compensator pole in order to make the new design point as a part of root locus. So angular contribution of minus 7.31 degree is the required from the compensator pole. Dear students, after finding the required angular compensation required from the compensator pole, we will use the geometry to find out compensator's pole location. Now using figure and applying trigonometry, we get the result that compensator pole will have a location of minus 42.69. Now in order to justify our estimates of percent overshoot and settling time, we must show that our second order approximation is valid. Students, now to perform this validity check, we will search for third and fourth pole of the closed loop system. Third pole is found beyond minus 42.96 and the fourth pole will be between minus 5 and minus 6 as shown in the figure. Now for this region and again equal to that of compensated dominant pole, which is 1423, we will find that a third pole and fourth pole are at minus 43.8 and minus 5.134 respectively. Since minus 43.8 is more than 20 times far away from the real part of dominant pole, so the effect of third closed loop pole is negligible, where the fourth closed loop pole is at minus 5.134 and it is close to the 0 at minus 5. So at this point we have pole 0 cancellation. So we conclude that our second order approximation is valid. And with this, our first lead compensator is completed for the given system. And second and third controller are designed with the same procedure by placing a compensator 0 at minus 4 and compensator 0 at minus 2. Rest of the steps are the same. Dear students, the dominant pair location, the transient specification, location of 0 and location of other poles are summarized in this table. For uncompensated system, for lead compensator with 0 at minus 5, for second lead compensator system with 0 at minus 4, and for third compensated system with 0 at minus 2. Dear students, this figure represents step responses for uncompensated system and 3 lead compensated system. You will observe a clear difference in the response of compensated system with uncompensated one. Now if any of you have any questions, please ask.